Last time we were talking about radioactive elements, and we said that radioactive elements they undergo what we call a radioactive decay. So, what is that? Actually, radioactive elements they do emit radiations, and these radiations are due to their unstable atomic nuclei. So, their nucleus is not stable at all. So what happens is that the nucleus undergoes reaction and emits either a proton or a neutron, because we know that in the nucleus there is what? Protons and the neutrons, right? Okay. So radioactive elements, so radioactive elements in there, those they do emit radiation. So these they emit radiation, and the radiation is due to their unstable atomic nucleus. Okay, so their unstable atomic nucleus that does release fast moving particles and energy. Plutonium, uranium, and radium, these are the most radioactive elements in the periodic table. So when we talk about radioactive decay are the different types of radiations an atom can undergo to get to the perfect ratio of the protons and the neutrons, because in the process it will be losing protons and it will be losing neutrons in there. So this is why radiation happened. Radiation happened again because the nuclei is not stable. The nucleus is not stable, and there's a lot of attractive forces between the neutrons and the protons inside the nucleus. And because of the lack of stability of the nucleus will try to be more stable. And for that, it will shoot up either a neutron or a proton. And this is going to be in a form of rays. Okay? It's going to be in a form of a radiation. So, types of radiations. Another word for radiation is decay. So, when we say radioactive decay, it's the same thing as radiation. So, it's the type of radiations the nucleus of the radioactive element shoots in order to achieve that stable number of protons and neutrons. So let's say, for example, if we take a radioactive element. Now we know radioactive elements are very dangerous because they emit radiation that we cannot see, right? So when we want to test any radioactive element, we cannot just put the radioactive element without a shield, right? It needs to be in a shield. Here, the shield is a lead box, a thick lead box. So you take a thick lead box, you have your radioactive element in there, and then there is a hole where that radioactive element can shoot protons or neutrons, shoot radiation. Of course, that path needs to be secure. It's open to the atmosphere. It needs to be secure. So let's say, for example, if you take a radioactive element in there and we allow it to shoot its radiation all the way through a detecting screen, what we will see is a spot in there on the screen. This is what we will see. We will see a spot here on the screen. Now, the spot on the screen or the radiation on the screen will have no charge at all. And this is called gamma radiation or gamma rays. So the gamma rays, these are rays that have no charge. This is a type of radiation, a radioactive element um, undergoes through its process of decay. And the gamma rays or the gamma radiations, they have no charge whatever. However, the scientist wonders, okay, is there any other rays other than the gamma rays that appear on the screen and they cannot see or detect? Well, in order to know this, If there's any other rays, these rays have to be charged. So what they did is that they added a charged plates, a positive and a negative plates. These are magnets, you guys. Okay, so these are magnetic charged plates in there, and they allowed that radioactive element to shoot radiation again. So now they noticed on the screen two additional rays, a gamma ray, an alpha ray, and a beta ray. So the alpha ray was attracted down underneath the gamma ray where the negative charge plates are. This means that the gamma ray is what? Positive or negative? Remember, opposites, they attract each other. Okay? Negative charge, same charges, they repel each other, right? So what do I have here? If I have a negative charge in there and I have an alpha ray which is in the same vicinity as the negative charge, what does that mean? The alpha ray has to be what? Negative or positive? Positive, because opposite, they do attract each other. So the alpha rays is a positive charge ray since it is attracted to the negative plate. And then the beta rays, these are negative charge rays. They are negative charge radiations, and they are negative since it is attracted to positive plates. These are the main type of rays: the beta rays, the gamma rays, and the alpha rays. These are the main type of rays, the or radiations a radioactive element undergoes. Of course, there are others, okay? But these are the three main radiations. And these are three main radiations, they have different charges. So let's go and talk about each one of them. Let's start with the alpha radiation. Alpha radiation is called an alpha decay, okay? And we represent an alpha radiation by the symbol alpha, by two protons and four mass number, okay? So what is an alpha radiation? An alpha radiation happens whenever the nucleus of the radioactive element loses two protons. So we say lose or give off. It loses two protons, and two neutrons in there. That is equivalent. So losing two protons and two neutrons, that is equivalent to an atomic or mass number of 4. This means that the nucleus will lose a helium atom, because if you take a look at the periodic table, helium does have an atomic number of 2, meaning that two protons in there. It does have two protons, and it does have a neutron of 4. 4 minus 2, this is 2 in there. So this means that the mass number is 4. So it means that the nucleus of a radioactive element loses a helium atom. Does lose a helium atom. Helium atom is equivalent to an alpha atom, same thing, and we represent it as an alpha 42, or we represent it as a helium 42 in there. If we look at this schematic, we start with a radioactive element. Okay, so we start with the nucleus. This is the nucleus of the radioactive element. In the process where that nucleus undergoes an alpha decay, that nucleus will become another nucleus that is short of, it lost two protons and two neutrons. So the nucleus becomes another nucleus. Think about it. So the element is different now. The element is completely different. You start with an element, and then during the process of the decay, you get another element, and then you get radiation. The radiation here is the alpha particle, which is equivalent to helium 42 atom. Guys, alpha decay is very weak. It cannot penetrate a piece of paper. Okay, so alpha decay is very weak. It cannot penetrate a piece of paper. So we can see that alpha decay is not very dangerous, okay? Because if you put a piece of paper in front of that radioactive element, just going to block the radiation. The radiation will not pass through. Beta radiations. We call them beta radiations or beta decay. These are two types, okay? There is more, but this is what I want you to know. I don't want you to know more than that. There are two types of beta radiations or beta decay. There's a B minus and a B plus. So let's talk about the B minus a bit. So B minus, which is the beta decay, it does consist, because we know that the nucleus of the radioactive element, it's going to shoot particles in there, right? And those particles are going to be our radiation. So in case of the beta decay, it does consist of stream of beta particles. What are beta particles? Beta particles, these are identical to an electron. And whenever we want to represent them, we represent them as either a regular electron, okay? This means that we take the nucleus, we allow the nucleus to lose an electron. So if the nucleus loses an electron, this is called a beta radiation or a beta decay. So this is an electron, or we can represent the beta decay by beta minus 1 and a 0. After all, the nucleus and there, or the molecule is, or the atom is losing an electron. It is losing an electron, or we can represent it as a B minus. All of those are representation for beta radiation. So during the process, you start with a radioactive nucleus. That radioactive nucleus, if it undergoes a beta decay, it is going to lose a neutron and it is going to gain a proton. So this one is going to lose a neutron and is going to gain a proton. And in the process, it's going to shoot an electron. In the process, it's going to shoot an electron, which is going to be a beta particle. This is called a beta negative decay. Normally in the reactions, whenever I want to ask you, let's say, for example, if I ask you this radioactive atom undergoes a beta decay, if I don't specify, then it is B minus. If I specify it, then I would say it is a, let's say, for example, it is a beta plus decay. Another word for it, it's a positron radiation, and this is what we use actually. We use a positron radiation. So positron radiation, this is another form of beta decay, but now the stream of beta particles will represent an electron with a positive charge. These are called positrons. So you have electrons that are negative, you have positrons, these are similar to electrons, but they are positive. These, they are represented by a simple electron with a 0 and a plus 1, or B0 and a 1, or B plus. Okay, one thing I forgot to mention, so let's go back to the alpha decay. Let's go back to the alpha decay. So if I look at the alpha decay in there, alpha decay, I am losing 2 protons and 2 neutrons. So if I look at the alpha particle, which is similar to the helium atom. So the alpha particle is the helium atom, same thing. I can represent it by an alpha or a helium-4 2. So if I am looking at this, then what is the atomic number of the alpha particle? What is the atomic number of the alpha particle? So 2 is the atomic number, and the atomic number represents the number of protons. I don't care about the electrons. Remember, we're working with the nucleus. So over here, I do have 2 protons in there. So the alpha particle contains 2 protons that the nucleus, the actual radioactive nucleus, lost. Okay, so what's the mass? What's the mass of the alpha particle? 4. The mass is 4. So here 4 represents the mass of helium or the alpha particle. Helium or the alpha particle. So the alpha particle does have a mass, and its mass is equal to 4 atomic units, which is equivalent to that of the helium atom. Okay? For the beta, what is the mass of the beta particle? The beta particle is represented by an electron, 0 and -1, right? So what is the mass of the beta particle? Does it have a mass? No. So the beta particle has no mass in there. So this one has no mass. What about its charge, you guys? What about the charge of the beta particle? Here it is negative. So it is a negative charge. Negative, why? Because that beta particle is made up of stream of negative electrons. And it's the negative electrons that are giving the beta particle its or beta radiation, its charge. Okay, for the positrons, it's still going to have no mass. So there is no mass for the positron radiation, and the charge for the positron radiation is a +1 charge. Okay, so for the positron radiations, we do represent them as beta 01, E01. You choose whatever you want for representation, but just guys be familiar, okay, with all of these representations. Now the gamma radiations. For the gamma radiations, these they do occur whenever we have a strong nuclear forces that are holding the nucleus together. So if you look at the nucleus, we know that the nucleus is made up of the protons and the neutrons, right? And the protons of the neutrons, we call them nucleons last time. So these protons and the neutrons, they are held together by this excessive force in there. There's a lot of force in there that is holding those together, which is going to be the components of the nucleus in there. Even though you don't have this excessive force, those protons and the neutrons try to wiggle a little bit, okay? So they wiggle underneath their force, and then when they do this, the energy is going to be given off, and that energy that is given off will be in a form of a gamma radiation. Guys, gamma radiation is a huge amount of energy. It does not have a charge, but it is a huge amount of energy, and that energy is similar, very similar to X-rays. It's very similar to X-rays. And we know that X-rays can be stopped by what? How can you stop X-ray? You know, when you want to go and do an X-ray, they give you a shield to wear, right? Okay, what is this shield made up of? Lead, exactly. Now, the thickness of the lead varies. So you gotta be very careful of the type of radiation that you're working with. So I'm talking about X-rays. Here, this is gamma radiation. So for gamma radiation, to block a gamma radiation, you need a thick piece of lead, okay? You need a very thick piece of lead in order to be able to block a gamma radiation. Another way to block a gamma radiation is soil, a thick level, a very thick level of soil. This is why radioactive materials, they do bury them under soil in there, and they cover them with concrete as well, either lead or concrete, whatever is cheaper. The concrete needs to be a very thick concrete, okay? There are other types of radiations other than the alpha, beta, and the gamma radiation. There are two types, which are the neutron radiation and the electron capture. The neutron radiation, it's the stream of high energy neutrons that are emitted from the nuclei of the radioactive element. And the neutron radiation, it is represented by an N1 and a 0. So it does have it does have a charge of 0. So the charge here is going to be 0. and then the mass of the neutron is going to be equal. This is going to be the mass number. So the mass is going to be 1. So far, um, the alpha radiation has the highest mass number among all radiations. Okay. Now, electron capture. Electron capture is different. Electron capture is, this one has no stream of particles. Instead, as the name says, it's an electron capture. Where are the electrons located? Outside the nucleus, right? This is it, outside the nucleus in there. So what happens is that an electron from outside the nucleus is withdrawn to the nucleus. This is called electron capture there, where it can combine with a proton and you form a neutron. This type of decay is normally represented by adding an electron to the reactants. So this one is represented, we're going to have an example on each one of those, okay? Represented by adding an electron, okay? An electron that has a charge of E0 and -1. So the mass of the electron is 0, the charge is -1 to the reactants. What does that mean? This means that whenever you are doing electron capture, you take the radioactive element, you add an electron to it, and see what are you going to get. Okay? Now, nuclear reactions. We did talk about chemical reactions. And we said that with chemical reactions, whatever you start with, the elements that you start with, you're going to get them. Okay? Not in the same form, but these elements, this is called the law of conservation of energy. So the elements that you start with, you're going to get those elements in a different form. So nothing is lost in there. With the nuclear reactions, this is completely different. Whatever you start with, you don't get. It decays and it becomes another element. So all particles that are involved in nuclear reactions, we're going to represent them as usual as we represent them in the periodic table. You do have an atom in there, so you represent the atom. You represent it by the mass number and the atomic number, okay? So we're going to represent them as the mass number and the atomic number. The mass number is going to be on top. The atomic number is going to be at the bottom. What we're going to care about is the atomic number, you guys, because this is how you're going to locate your element in the periodic table. The rule says that as we balance chemical reactions, we're going to balance nuclear reactions. But here, for nuclear reactions, we care about balancing the atomic number and the mass number. So the atomic number in the reactants has to be the same in the products, and same thing for the mass number. The mass number in the reactants have to be the same in the product as well. All of these radioactive elements, they do have an unstable nucleus, right? Because the nucleus is emitting radiation. So for the nucleus to emit radiation, that's why we call them radioactive, because they are unstable, they emit radiation. So when an unstable nucleus of a radioactive element emit radiation, what you're going to end up with is a product. That product will be a different element than what you started with. That element in the product, we're going to call it a daughter nucleus. So whatever is going to form in the product, we're going to call that a daughter nucleus. So this is the nucleus of the new element that is formed. It's going to have a different nucleus than the one that you started with. Because, of course, the nucleus is going to have maybe less neutrons, more protons. So it really depends on the type of radiation or decay that nucleus undergoes. So let's go ahead and have an example just to show you how to solve these problems. And did I print that extra problem set for the radioactive decay last time? Yeah. Okay. So here's what I'm gonna do. I'm gonna leave this for you to solve it. It's not homework. I want you to solve it at home based on the examples that we are doing today. Okay? And then next time, just giving you some time to solve it, and then next time we are going to go over it. So, okay. So when we approach these types of problems in there, definitely you will have the atom that you are starting with. This is a bromine 84. What is 84? What is 84? Is it the atomic number or the mass number? What did we agree last time? It is the mass number. I don't care about. It's the mass number I don't care about. So here's what you do. Here's what you do. You look at just the bromine. Just the bromine. Forget about the 84 and look at for bromine in the periodic table. Okay? What is the atomic number of the bromine? Okay. So to locate the element, you have to ignore the mass number. So that bromine, that 84 that you see, this one is the mass number. Guys, please do not use it when you're looking for a bromine. Just look for a bromine in the periodic table. And the bromine does have an atomic number of 35. So we're going to go ahead and write 35 over there. See what I did? So you look for the bromine, you look for, so look for the atomic number of bromine. And then they gave you that one of the isotopes, this is why they are giving you the 84. What is 84? 84 is the mass. The mass of what? It is not the mass of the bromine, all the bromine is the mass of one isotope of that bromine, right? So one isotope of that bromine has 84, so we're just going to go ahead and put an 84 over there. The question says that bromine 84 decays, and when it decays, so it decays by emitting. See that emitting? Emitting means that the radiation is found in the product. Make sense? So it's going to emit, so the radiation is found in the product, it's going to emit a beta particle. There is a table for all the radiations, and this is the table here. Now that table, I'm going to include it in the cheat sheet for this chapter, so you don't have to memorize it. All what you need to add on this table is the electron capture, because I don't think it's added. So the electron capture there, capture. And for the symbol of the electron capture, we're going to say over here, add an electron to the reactants. Okay? And electron capture has a mass number of 0 and a charge of negative. Okay? And this is a negative electron. Okay? So this table over there, you're going to have it in the exam so that you know the symbol for each. So I am emitting a beta particle. So if I am emitting a beta particle, you can represent the beta particle by either beta 0 and negative 1, or you can represent it by an electron 0 and negative 1. Okay? So here's the thing. Now comes balancing of the nuclear equation. Remember what I said. The atomic number and the mass number of the reactants has to be the same in the product, right? So whenever bromine emits that beta radiation, it's going to become another element. We don't know what element that is, but we know the radiation that it is emitting, which is 0 and negative 1, right? So I'm going to say, okay, I'm going to form a daughter nucleus or a daughter element. I don't know what that is. So I'm just going to put it as an X. But now the sum of the atomic number and the mass number, they have to be the same as 84 and 35. Does that make sense? So X now should have what atomic number? What atomic number? 36, right? So 36, because I would go, okay, I would go 36 minus 1, this is 35. Honestly, it's really very simple. It can get some complicated, yes, but if you follow this way, it's not going to be complicated. You can easily figure out what the element is. Now, I know that I did nothing to the 84, right? Because this is a 0, so that is going to be 84. Now I go to the periodic table and I want to figure out what x is. So to do that, guys, do not look at 84. Always to locate any element in the periodic table, we look at the atomic number, okay? So you go to the periodic table, locate an element that is 36 atomic number for me. What is that? It's going to be krypton. So X over here, we're going to take that out and we're going to say, okay, we are forming krypton. So in the nuclear reaction, what we did over there, we changed the atomic number. This is what we did. So in the nuclear reaction, we did change the atomic number. So it is not a bromine anymore. It is a krypton in this case. So the atomic number is changed. And Br35 becomes krypton 36 over time, because we know that radiation takes time in there. So over time, as it gains one proton of one proton, exactly. So the bromine will lose one proton, and that proton will go to the daughter nucleus. Are we good? Okay. So let's try to do the second one. So we're going to start with samarium. This is SM. SM in the periodic table has an atomic number of 62. Its isotope is 148. This is what is given, okay? I don't know what radiation it is, but I am forming the daughter, which is neodymium or neodymium. It is 144, so it is 144 in there. And if you look and see in there, so it is 144. It is given neodymium 144. So neodymium in the periodic table, Nd is what? It is 60, right? So we're going to go ahead and put a 60. Guys, you're not guessing. You're figuring it out from the periodic table. So I figured everything here from the periodic table. I just want to balance the equation to see what type of radiation did I lose. So between 148, so I know here that I need to add 4, right? I need to add 4 up there. And I need over here to add 2. That is equivalent to an alpha radiation. Correct this. So this is an alpha radiation. Or I can write it down as helium 4-2. Okay? Either one of these representations is true. So what I did over here is that I lost 2 protons and 2 neutrons. This is what I did. So here we lost 2 protons and 2 neutrons during the radiation. And what I formed is the daughter that has a mass of 144. So this one is the daughter nucleus that has a mass of 144. So the emitted radiation must have a mass number of 4, okay? This is why the emitted radiation in there must have a mass number of 4. This is the emitted radiation. Radiation must have a mass number of 4. Must have a 4. Therefore, the emitted particle is, or the emitted radiation is an alpha particle. So the complete balanced equation is samarium. It does undergo an alpha decay to produce the neodymium. Okay, Let's do another one. Now it's electron capture. So for electron capture, we are going to add an electron to the reactants. Okay? So we're going to add an electron to the reactants. This is what an electron capture is. Because you know that the electrons, they are not located in the nucleus, but they are drawn from the outside to the nucleus where the nuclear radiation happens, or the nuclear decay. Okay, so tungsten, what is the symbol of tungsten? It is W. What is the atomic number? 74. Does have a mass number of 175. Again, electron capture, you guys, means that this is the only case where I am going to add to the reactants. All the decay happens where I should show the radiation in the product, except this one, because this one is not a radiation to start with. This one is not a radiation, so I would show that in the reactants. So I am adding an electron. I am adding an electron to the nucleus, okay, to the nucleus of the tungsten. This is what it means. What I'm going to form? So what should I form? The element that I'm going to form needs to have an atomic number of what? 70, 74 minus 1. This is a negative 1. Do you see it? So I am subtracting 1 from 74. I am not adding 1. So it cannot be 75. If it is 75, then the equation is not balanced, because you will have 73 on one side and 75 on the other. Okay? So the element needs to be 73. So 73 is a representation of what element? It's the tantalum, exactly. So this is tantalum in there. So the daughter is tantalum. This is the daughter of the tungsten. Okay? And what about the mass number? It remains 175. Are you getting it? Okay, is it hard? It's a tricky. It's a tricky, so you gotta pay attention with your calculations in there. Okay. Let's do this one. Okay. Uranium 238 is undergoing. I did put this twice. Okay. An alpha decay. So we do have an alpha decay in there. What is the formula of the daughter nucleus that is formed? Okay. Take some time and do this. What is the atomic number of uranium? It's 92. It's 238. It's undergoing an alpha decay. So I'm just going to write the alpha decay as helium 42. You can write it as alpha 42 as well, okay? Plus, so whatever element that you're forming needs to have lower than uranium by a mass of 4, okay? And lower than uranium by an atomic mass of 2. So that is going to be what? It's going to be thorium. Thorium is 90, and it is 234. So if you go ahead and you add 234 plus 4, that will give you 238. And if you add 90 plus 2, that will give you 92. Okay? So we're going to get to thorium. Okay, so what we did over here is that uranium, that is the mass number. So uranium lost two protons, it lost two neutrons. Two protons and two neutrons, that is equivalent to a helium atom, in order to make thorium as the daughter nucleus. So this one lost two protons and two neutrons. Okay? Any question on this? Okay. So let's do the other one. Cesium 137 undergoes a beta decay. Write the nuclear equation. What is the atomic number of cesium, you guys? 55. It is 55, 137. Okay, so what is the charge of the beta decay? It's an electron, right? So you can either write it as an electron like this, or you can write it as a beta 01 like that. Guys, the representation is very important, okay? So either one of those can do the job, plus, okay, the daughter nucleus will have what atomic number? 56, exactly. So that will make it to be what? 56 is barium, right? So that is going to be barium in there. So notice that the daughter nucleus in there, it gained a proton. Okay, and remember in the process, one of the neutrons became a proton and gave up an electron. This is the definition of beta decay. One of the neutrons in the nucleus, it became a proton, and during that process, an electron has been given off, which is the beta decay. So that's barium, and the mass number is going to be 137. Okay? So again, you rely on the atomic number in order to figure out what element you are working with. And you search using the atomic number of that element in the periodic table. Sodium 22 undergoes a beta plus decay now. It's a beta plus decay. It's not a beta decay. So notice here, again, when it is a regular beta minus decay, I would say it's a beta decay. So it's a regular loss of electron. But if it is a gain of electron, then I would need to indicate the charge of the beta. So it is a beta plus decay in there. Guys, remember that in beta plus decay, we are losing an electron, However, the electron has a positive charge, okay? However, the electron has a positive charge. So the loss is going to appear in the product. It's not going to be in the reactants. So I'm starting with sodium. I know that sodium has an atomic number of 11. So I stop at 22. Okay. I am losing an electron, but the electron is positive charge. Okay. I can either represent it as an E or a beta. Okay. So E, or I can represent it as a beta 0 positive 1, you guys. Both are the same. Plus, what is the daughter nucleus now? Neon. It's going to be neon. It's going to be 10. So neon has an atomic number of 10 plus 1. 10 plus 1 is 11. Okay? Nothing is going to happen to the mass number. It's going to stay 22. So sodium, if we lose a proton, one proton in there, it will become neon.